you. I'd like to start off by just thanking ISNTD for hosting this great event and for inviting me to speak here today. So I'm going to be talking about the need to rethink neglected tropical disease diagnostics if we want to achieve elimination. So when it comes to the preventative chemotherapy treated NTDs, the diagnostic tools that have served us well for mapping and monitoring the great progress of the past decade are unfortunately insufficient to take these global programs through the finish line of elimination. And in fact, we need a complete reboot to the way that we've been thinking about diagnostics. And this is because the testing needs for NTDs are unique. Unlike large disease programs like TB or HIV, the goal of testing is not to make an individual diagnosis, but NTD testing is used to make a public health decision. And for the PC NTDs, these decisions are made by applying a diagnostic test in the context of a population-based survey to measure a WHO-specified threshold for the specific disease. And so for the elimination endgame, the NTDs need tests that are fit for purpose. And this requires us to make 4 key changes in the way that we think about, develop, and deploy diagnostic tests for NTDs. And the 4 changes I'm going to talk about briefly today are the recognition that specificity is paramount, the need to consider the context in which the tests will be used, a willingness to abandon the single test paradigm, and being able to adapt our decision rules to reflect test performance. Now, when it comes to disease elimination and measuring a rare event, it feels like common sense that one would need a highly sensitive test to detect those needles in a haystack. But it turns out that for the NTDs, it's specificity that determines a test's utility for endgame decision-making. And this is because population-based decision-making requires different thinking. So for example, let's take a typical program strategy for stopping mass drug administration. And so you would test a sample of the population and then compare the observed prevalence against a target threshold. And based on where that observed prevalence falls, decide if mass treatment should continue or if elimination has been reached. Now, the key here is this observed prevalence will be comprised of a proportion of true positives and false positives. And as disease approaches elimination, the proportion of true positives will decrease, while the proportion of false positives will increase, which makes it harder to interpret the observed prevalence. So to understand why specificity is key, let's take a look at the impact of test performance when prevalence is low. Specifically, what is the impact of sensitivity and specificity on the negative predictive value? And just for a quick Epidemiology 101 refresher, NPV, that's the probability that someone testing negative is uninfected. So we have 2 graphs here, and on the y-axis of both the graphs is the negative predictive value. And on the left, you can see I'm varying the sensitivity from 50% to 100%. And on the right, varying specificity from 50% to 100%. And really, the key takeaway here is that increasing sensitivity or specificity has very little impact on the negative predictive value when prevalence is low. And this makes sense because almost everybody in the population is, in fact, truly negative. But what happens when we look at the positive predictive value? And again, that's the probability that someone testing positive is infected. And here again, we have 2 graphs. This time, it's the positive predictive value that is on the y-axis. So let's focus on the graph on the left. This is looking at sensitivity. And you can see that as sensitivity increases, there is little change to the positive predictive value, as evident by the relatively flat lines you see. And in fact, it is prevalence and not sensitivity that has the greatest impact on the positive predictive value. But that positive predictive value remains pretty low. Now let's look at the right-hand side where we're varying specificity. If you look at that graph, you can see that the PPV increases almost exponentially with specificity. But it's not until you reach at least 95% specificity that you start to get a positive predictive value that approaches even 50%. So the key takeaway here is that specificity really is the main driver of your positive predictive value when the prevalence is low, and that minor changes in your specificity can dramatically impact your interpretation. So my second point is that we need to consider the monitoring and evaluation tool when developing new tests. And to illustrate this, let's take a hypothetical test and suppose it is 95% sensitive and 99% specific. So what is the probability that one uninfected person tests negative? This is just the definition of specificity, so it would be 99%. But what we really care about for NTDs is what happens when we test a population. So if we do a larger survey in order to estimate prevalence, how would this test impact our results? So what is the probability that 1,500 uninfected people test negative? And this is actually similar to the sample size that is used for a transmission assessment survey to stop mass drug administration for lymphatic filariasis. So while each uninfected person has a 99% chance of testing negative, the likelihood that all 1,500 people test negative is 99 to the 1,500th power, which is essentially 0. So even if the entire population were uninfected, with a test that has this accuracy, you wouldn't see 0. So how many false positives out of 1,500 would you expect? Well, the distribution of expected false positives is there on the left. And as you might guess, with 99% specificity and a sample size of 1,500, the most likely number is 15, which you can see from that graph. But more importantly, it would not be uncommon to observe 18, 19, or 20 false positives. And in fact, it's not until you see 22 or more false positives that you can start to rule out the likelihood that this is a chance finding. So coming back to the lymphatic filariasis analogy, for a sample size of 1,500, the critical cutoff for measuring transmission at a 2% threshold is 18. So even if elimination has been achieved and everybody is truly negative in the population, there is still a 20% chance that you would observe more than 18 positive results by chance alone. So clearly a test that is 99% specific is not sufficient for measuring a 1% or even a 2% threshold with some statistical confidence. And so this having inadequate specificity could prevent programs from demonstrating that elimination has been reached. So what can we do? Well, one option is to move away from this reliance on a single test. And let me start by giving an example of sequential testing, which has been used by a variety of public health programs, notably in the HIV world. So we start by testing everybody in your survey population with a first test, and this could be a rapid point of care test. And then only those who test negative by the first test would receive the second confirmatory test. And individuals who test positive by both tests are considered the true positives. And one could pick your test strategically so that the first one maximizes sensitivity, the second one maximizes specificity. And it can be shown that this approach can lead to a net specificity that is greater than either test alone. Now, alternatively, instead of 2 tests, one could consider 2 markers. So for example, a diagnostic that measures 2 different antibodies for the same disease. This is akin to parallel testing. And the detection of 2 or more markers for a single disease on one test gives the user an options for how they interpret the results. So one could interpret the results in a way that maximizes sensitivity by saying that a positive signal for either antibody means that the individual tested positive. Or you could choose to maximize specificity by requiring that both antibodies be present on the test in order for an individual to be considered positive. So consequently, one test could potentially serve multiple program needs. So the key takeaway here is that using 2 or more tests or markers in a sequential or parallel strategy can increase the specificity of the diagnostic approach beyond that of either test alone. And consequently, this can help to relieve some of the high specificity demands that are placed on a single test when we're trying to measure a low prevalence of elimination. But finally, it's clear that no diagnostic test will ever be perfect, and we don't want to let perfect be the enemy of the good. So when epidemiologists design a population-based survey to measure a threshold, the following 4 parameters are commonly considered. So that's sample size, the threshold, type 1 error, and power. And in the context of NTD elimination, we can think of power as the likelihood of identifying correctly that elimination has been achieved, whereas type 1 error is the risk of prematurely concluding that elimination has been achieved when in fact it has not. And so we can think of these as levers that can be dialed up or dialed down. And moving one, like realigning the threshold, will impact your other parameters. So for any survey tool, it's a balancing act of how to set these. But historically, the NTD programs have rarely taken into consideration test performance when designing these tools, which is akin to assuming you have a perfect test. And we know that that is, of course, not the reality. And so it's important that we modify these survey parameters to reflect the test performance. So for example, if a test is less than 100% sensitive, this can be accommodated by increasing the sample size. Similarly, if a test is less than 100% specific, the threshold for decision-making can be increased to incorporate the proportion of false positives, or you could decrease the level of acceptable power. So the main point here is that moving forward, disease elimination programs should consider adapting their M&E decision rules to account for test performance. So to conclude, the ability of the PC-NTD programs to stop mass treatment and have confidence that elimination is being maintained hinges upon the availability of diagnostic tests that are fit for purpose. And such tests will need to be highly specific to measure the low prevalence thresholds indicative of elimination, and just how specific will depend on the target threshold and sampling strategy being employed by the M&E tool. And if those specificity requirements are prohibitively high, then test developers should consider creative solutions, like combining tests serially in the case of a confirmatory assay, or in parallel by creating a multiplex test, and this can result in significant gains to net specificity. And then finally, it's important to recognize that no test will be perfect, and it's imperative that the M&E decision rules be adapted to reflect test performance in the field. And if we take these steps, I believe it is possible to have a diagnostic strategy that can get us through the elimination endgame. And so with that, I want to thank the organizers once again. Thank you very much.